Okay, thank you everyone for being here. And my name is Marcello. I'm a software engineer at Uber, and today we're going to talk about something we did during the last year to tackle the problem of mobile performance at Uber and what means mobile performance at scale of Uber. And so, first thing I want to ask is what's mobile performance? And I was looking at a lot of different definitions for this talk, and they're all very interesting, but I think that at the end, what we really want to ask is one simple question, that is, how well are we doing in offering the user a pleasant user experience when using the app? And then if you look at the data, we can see that there is a strict correlation between business metrics and app performance. This is also a very intuitive step. It's very easy to see the user that prefers to use an app that is smooth and not janky. Which are these possible app performance metrics? I just put a bunch of them here: CPU usage, battery usage, memory usage, frame rate. But also things like how much does it take? How much time does it take, like, to change from state A to B, for example, or like how much long takes a certain piece of code to be executed. Specifically about mobile performance, there is another problem that is about responsiveness. The user touches the screen and he wants to see a feedback that is in a certain amount, a specific amount of time. So we're a big company, and I just want to simulate an example. There is someone coming, an anonymous developer coming and saying, hey, my feature performs badly, it's janky, and I have no idea why. So let's see what we can do to help this developer. And this is what the Android documentation says. When the user touches a button, the API thread dispatches the touch event to the widget, sets a preset state, and then notifies the widget that it should redraw itself. This is what the Android documentation says, but let's see what it means exactly. So I just reported here, this is the simple math. We want to render a frame every 60 milliseconds. So what that means is that, well, let's say that we are rendering the first frame, and then we execute a bunch of work. And then at this point, we start to execute a long operation that takes more than 60 milliseconds. For example, in this case, we're skipping 3 frames. And then we draw another frame, some other work, frame, work, that's okay. So ideally, if we want to allow the system to draw a frame every 60 milliseconds and have this kind of feeling of like smoothness without any jankiness, we need to keep the main thread free and able to draw a frame every 60 milliseconds. Additionally, the Android documentation also says that the user expects a feedback about after 100 to 200 milliseconds. And this is pretty much another example. So we needed to show something after the user, for example, presses a button after 100 to 200 milliseconds. So what can we do to help this developer? There are already a bunch of tools that are out there. I just reported some of them, SizeTrace, TraceView, GFX Info. There is also a very interesting talk, the Google I/O this year, that was talking about SizeTrace. It was very, very interesting. And why not just use these tools? Well, we actually do use these tools. And we use them to find the issues in the app. But we also wanted to have, that was very important for us, something that we could use in production. And that we could use as well in a test environment. So let's see which are the requirements for this performance monitoring at scale. And what's the scale of Uber? Uber operates in 600 cities, 24/7, variety of devices, network conditions. We have multiple apps, multiple platforms, Android, iOS, hundreds of engineers, hundreds of commits every day. This is a very interesting point because it's almost impossible that to like check all the code that is committed from a performance perspective beside the code reviews. But the most interesting thing is also that all this code is for 2 platforms, Android and iOS. So let's talk about some of the requirements. First of all, it has to be easy to integrate. Ideally, it should require minimum possible amount of work. Developers want to focus on the features. Should be compatible with multiple build systems. This is a very specific thing to Uber because we migrated from Gradle to Bugs in the Android environment. So we needed it to work with both build systems. Should gather metrics, like the ones we mentioned before, so CPU, frame rate, but also measure duration of parts of the code. Should be easy to plug a new metric provider because there could be some custom metrics to trace. It should have a minimum impact on performance themselves. Of course, there is always an impact, but we just want to minimize it. Additionally, we want to be able to dynamically decide which parts of the code to trace and target only the parts that we need. And as well, we want to have this tracing bot from production and test environment. So we came up with this idea that about what to do in this for tracing, and we came up with this performance tracing SDK. We named it Ferret. Let's see how this works. So there are two main concepts that also are two main API. One is the tracer that is able basically to measure the duration of the two markers, between two markers in the code. And the second thing is that we have monitors. Monitors are basically, they encapsulate the logic to gather a metric, like the CPU, the frame rate, etc. A bunch of requirements about these ones. We want to have an output interface. This is important because we may want to write to a file, or we may want to make a network request and send this data to a backend. We want to choose which code should be traced or not at runtime. And we should be able to tag or trace, or allow a tag to trace or log some values. About the monitor instead, this is there are some events in the system that are event-based, like for example, when the battery changes, this is notified through a broadcast receiver on Android. So these are event-based, but there are other things like, for example, reading the CPU usage of the last second. For example, we may want to do this every second, or like the frame rate. Again, this is the same as the tracer. We want an output interface, and then we want to be able to turn them on and off only when needed. So let's see how the tracer API work. I want to start with a simple introduction of what we call trace and what we call span. So let's say that each span, basically in this slide, it represents a function. And we also have the concept of the parent-child relationship. So A is parent of B and B is parent of C. A full group of spans of the same sessions, it's simply called the trace for us. This is the architecture of the tracer. It's fairly simple, actually. There is a main entry point that is called the tracer manager. This is initialized with a bunch of objects, and it creates this object called span. That is what we defined before, and it represents the execution of a function or just the execution of code between two different markers. There are a bunch of configuration objects that are needed, and this is because we really wanted to be able to tune it according to the app and the use case. This is a data flow. We just check if it's enabled. You can expect that there is something that comes from the backend and says yes, trace or not. We call tracermanager.start. There is a configuration interface that says, hey, this is the span. Should I proceed tracing it? So you can expect also here something from the backend that says what has to be traced and what is not. Let's say yes. At this point, we create this span, we execute the code, and then we simply call finish. And then we pass this span object to our interceptors and reporters. In the specific case of the tracer, there are two different tracers. One is the auto tracer that is used for function tracing. And it's done automatically. You don't need to do anything besides some configuration. We basically automatically inject some code in some parts of the app. And I'm going to show how in a bit. And the second part is the manual tracing. This is more like to trace logical operations that are not just self-contained in a function. For example, you may want to trace the duration for the Uber app. Could be, for example, since you call a ride, for example, till the state in the app changes and to receiving the message from the backend. So how does it work, this bytecode injection? Let's say that you have a simple function that is executing some code. That's just for an example. Bytecode injection, basically, it's with our transform, is basically going to inject an instruction at the start of the method and at the end. It's simply called the start And as arguments puts a bunch of specific information about the function, like the class name, the full qualified class name, the method signature, and a bunch of other things that are used to describe the function itself. And then at the end, we just simply call finish. This is how you basically configure it. It's fairly simple. You just need to apply the plugin, basically, and then you create this performance config file. We use an external file because we are also, as I was saying before, we are also compatible with Bach through OKBach. That does basically a translation from the Gradle file to the Bach configuration file. The manual tracing instead requires the developers to actually put these markers in the code, and then they are also able to set tags or log some events. And it's pretty much as it's shown in this slide. As I was saying, also there is we have a trace of the concept of which functions are executed as parent and which functions are the children. And this is done through something that we call the parent span handler. Basically, the way in which this works is that we have simply a thread map, and inside this thread map, basically we keep a stack of the current opened span for that thread. And when the span is completed, we simply remove it from the stack. This way, we are always able to reconnect the span to the previous executed one. If we log in console one of these spans, this is pretty much what we see. So we have an ID, an operation name that is, in the case of the auto tracing, it's basically the full qualified class name and then the method signature. We have a parent span. This is basically the ID pointing to the parent function, if existing or null otherwise. A bunch of tags that some of them are automatically added, but it's also possible to set them at runtime. Other interesting things here, you can also find the Java file name where we injected the code, and even the line number for the method. This is useful if you want to reconnect the performance information back to the file that created that where this code was injected. And then we have duration and start time. This is how the configuration in the JSON file is set. Basically, the main important thing here is that we define what code we want to trace based simply on a set of regular expression. And then we basically post-process this. We have a post-compilation step that basically goes through all the compiled classes. And then if the full qualified class name matches the regular expression, then we inject the tracing instruction with a tag. And we then use this tag to match it back with our backend configuration to say turn on and off the tracing for this piece of code. The same concept is applied for blacklisting actually classes as well, because ideally you want to avoid tracing, for example, views on Android or code that has to be very performant. This is possible also through annotations. So same thing, we can define a tracing strategy that can be a blacklist, a whitelist, and then basically we have this annotation here, do not trace, that basically will just say to the post-processing step just to skip the method. And then we have these two other annotations, start span and stop span. This is basically a shortcut to automatically inject a manual span, start and stop. As I was saying before, we have also a configuration system that says what should be traced and what shouldn't. And this is done through two simple interfaces that can be defined, and by default they're always returning true here. But we can basically match this class name and method names, or simply match some tags that we create at this post-process step. The same is valid for the manual tracer configuration. So this is the way in which we basically estimated the impact of ferret. Basically, let's say that you have two functions, foo and bar, and foo doesn't know the duration of the performance SDK itself, but knows the duration of bar, and bar doesn't know the duration of the performance SDK again, but knows the duration of itself. So if you simply subtract them and you assume that they are defined as shown on the right, you basically find the duration of how much time we spent in ferret. And so this calculation basically showed that the tracing takes about 1 millisecond per method on a 2012 year class device. And we use the Facebook year class classification That means that it's a device that in 2012 was considered a high-end device. So the total impact can also be tuned through the configuration. Let's say that in the same interface I showed before, you put a random and say, yeah, I just want to trace one function every 100, every 1,000, every 10,000, for example. So thing is that if you trace all the code, basically you put a regular expression that says trace everything, the impact can be noticeable because you're basically adding 1 millisecond, especially if you, per method, especially if you trace getters and setters. So getters and setters are super fast, right? So for example, they are in the order of a few microseconds, depending from the device, of course. But then we realized that we also wanted to give developers a tool to instrument their local builds. And so we created this thing called the light tracing, and it's basically a light version that can be configured through this flag in the configuration file called the create trace file. And then we have a build type that just uses a configuration with this flag set to true. So the light version basically can be used only for local debugging. And what it does is that skips all the ferret pipeline and print each span in the logs. And then the overhead for this is quite low, and it's just a few hundred microseconds. So additionally, we wanted to make this very easy to use. So we built an IntelliJ plugin that reads all this printed span and then creates a Chrome tracing file. That is basically the same interface of size trace. So what you have at the end is a local function profiler where you can see all the functions being called here. You can also see the stack trace, basically how it evolves over time. And then we combine informations like at the bottom of this screen, for example, we attached these are the manual spans. So we see exactly what code was executed between the manual spans. Additionally, at the top, there is the output of a monitor we're going to see in a second. But basically, this is one of our indicators for understanding if the app was dropping frames. And in this case, we are pushing some work in the main thread. So the application enters in something we call dropping state after skipping a certain number of consecutive frames, and then recovers from the dropping state after drawing a certain number of consecutive frames. Let's see a moment at the monitor API, how do they work. The architecture is similar to the one of the tracer. Again, here, very configurable, and there is a builder where we set all these objects there, and then in output it generates this monitor. Specifically, this is the data flow. Again, it's enabled or not. Then we have a metric provider that is basically the main interface that provides the metric. This is passed in the monitor that just decorates the output of the metric provider with a bunch of useful information, like, for example, the time since the last gather metric, or some other informations. And then we pass this to interceptor and reporters. So this is pretty much what's the definition of a metric provider. It has simply a name that says what's the name of the metric we're collecting, and then there is an observable that returns basically all the measures for this metric. What's the initialization for the monitors? This is it, basically. Just 5 lines, and in the first case, we are creating a frame rate metric provider, and then we're saying we want to repeat this every second, and we are passing some reporters interfaces. And the same for metric provider. We can collect this every second again. As you see here, there is also an enable, and there is also a disable method, and you can expect again that the backend is able to turn on and off this kind of tracing. This is what metric basically contains, and it's an ID again, the name of the metric, and an array of measures. For example, frame rate, what was the longest drop between the different frames, stands on tags, and then when the metric was actually measured. I was mentioning before the frame drop monitor that tells us how much time we spend in a junk state. And I mentioned this before. It's basically we drop a certain amount of frame in a time range, and then to exit the junk state, basically we have to draw again a certain amount of consecutive frames. Okay, how do we visualize this data? This is probably the other half of the problem, because performance data can be very interesting, but we also need to represent it in a manifold way. So there can be the local visualization, that is what we were talking before, But it's more interesting for us to look at this data in an aggregated way. So we can understand things like, for example, suppose that you put a manual span. So 2 markers in the code. This is actually a real use case. We have a span that is called the dispatch to route duration. And then we say that, hey, at some point, this duration can be improved. What can we do? So we started working on the code, we refactored, and then we started shipping some progressive updates. What we saw was that the duration of this span was simply going down. And ideally, you can expect that there is an alerting system that says, hey, now this duration is going up again. Should we do something? Should we investigate? Why is this happening? This is, for example, a possible usage. Or another one that is another real use case is that we measure, for example, how much object we instantiate when the app gets created. And we were checking, hey, can we improve here? What can we do here? So we started checking the memory usage, and then we made some fixes. And then at some point, we basically were able to measure that there was a huge improvement here between the 4th and the 5th bar. And we are now basically able to make sure that this is always a metric under our eyes. There are other kind of analysis that you can do, especially if you have more data that comes maybe from a test environment. And so you can combine, for example, auto tracing with manual tracing. In this case, for example, you can see all the functions that were executed between the manual traces. And maybe if you're trying to improve a piece of code and then you have this manual trace, you can say, hey, these were the functions with where we spent most of the time, maybe on the main thread. Now, I also wanted to put here an example of something of the light tracing I was talking before, because I think it's very interesting. Suppose that you have a very simple application. So we basically initialize this light tracing, our monitors, and then we say start a manual span. This is pretty much an activity on create. So we set a bunch of things. So we're using Dagger, and then we the first layout change we set basically we stop the span. Additionally, we have a bunch of other spans like on resume, on pause, and then we have a fab button. Basically, it's a button that is triggering a 2 seconds thread sleep on the main thread, and it's triggered after 1 second. This is just for an experiment to show it. Actually, let me go forward here. Okay, let me show you what this looks like. So you can expect it to have something like this. Simple app, you start it, it's loading a bunch of images. Now you scroll, it's fine. And now you click on the fab button on the top. And now it's frozen. And it's recovered again. So basically it was blocked on the main thread for 2 seconds. So the app is very smooth, but right now it's fully instrumented with the light tracing. And the impact is noticeable only according to the, it depends how much code you are tracing. So, and the code that should be traced is specified in the configuration file. So you can tune it for the part of the code that you are investigating. So at this point, I want to show you what's the produced trace. Whoop. Okay. So for the example that we ran before, this is what the local profiler gives in output. So at the top, you have the frame drop monitor. Basically, this was when we started the app. And okay, so this was the initialization, and then the app was starting. So basically, nothing was drawn, and we were dropping all the frames. Here at the start, you find, for example, okay, initialize monitor took here 80 milliseconds. There were no subcalls. Then we called here on create for the activity. Here, there are a bunch of subcalls that we can see. For example, Dagger was injecting some code, and then this took about 1 millisecond. 1 millisecond. It's fine, not that much. Some other stuff here, and so this is very interesting because you can measure the duration of everything you are injecting through Dagger, and you can also see if you're instantiating some big object that is taking too much time. On the top of this, I also put this span, this manual span that is app start. So this is basically starting at the marker I put, and then it's stopping here when the layout on change listener was called. Okay, this is instead the adapter. So at this point, the app started, and it started drawing frames. We find a bunch of calls here. It's basically get on it and count. It was the adapter that was converting the list of images to basically actually image view. This is the other span we had, activity foreground. While we were scrolling, of course, the adapter was also doing the work of binding the view, creating the view if it was necessary. At this point, we clicked on the fab button, and the main thread basically was stopping for 2 seconds. So the whole duration of this function is about 2 seconds. And this is also the manual span that we appended. And then it recovered and started drawing again. And then we basically closed the app, and the activity foreground span was created. So this is a very interesting tool. You can basically configure it if you want to trace, for example, Dagger, if you want to trace, I don't know, any other library, and or simply if you want to understand a very specific part of your code. At this point, so we are moving toward open sourcing all this part, Ferret, and just let's say that there is still the same anonymous developer who wants to use Ferret in his application, and basically we're working on it, and we are aiming to open source this in the next coming months. And that's it. This is what I wanted to talk about. Is there any question? No? Okay, cool. Thank you for the attention then, and I hope you will use it as soon as we open source it. Thank you.